Hello and welcome to another tutorial. We are looking at the for loops, and we saw that for any collection of items, for example, an array or any of the Java collection objects like a list or set, you can use a enhanced for loop. Remember, there is no such thing as enhanced while loop, right? But we have the for loop, which is called the enhanced for loop or for each loop. And I showed you that Eclipse also has a for each template that you type it, you press enter, Eclipse creates the syntax for the for each loop or enhanced for loop. And then you can basically iterate through all the elements of the items. So that the limitation for enhanced for loop was that you end up with iterating through all the elements of the collection. For example, if you have an array, you end up iterating through all of them. If you just want to iterate through some of them, for example, arrays are index based, right? Or lists in Java are index based. So you can use the traditional for loop that has a loop counter and then specify which indices to loop through, right? But with the enhanced for loop, you're limited, or you end up with iterating through all the items, right? So that's the limitation. What I would like to show you is the bytecode. So what happens in the bytecode for the enhanced for loop? Public static void test6, and let's say we have this int array, right? And then what we're going to do, I showed you previously just index based iteration through the array, or basically a enhanced for loop. So this is the enhanced for loop, right? Let's see what happens in the bytecode. So I'm going to run test6. And if I run this, it's going to print all the elements, right, 1 to 10, that are inside this array. We're using this colon, which means in or inside. Now, interestingly, in other programming languages, such as Python, there is actually a keyword called in, which you use instead of this colon. In Java, there is no keyword in. You use this basically colon, right, for this enhanced for loop syntax. So let's look at the bytecode. So I'm going to go to Navigator and then look at my class file for the for loop, open it with class file viewer. Let's put this side by side and go full screen. And we're looking at test6. All right, where is test6? So test5 here and test6. Now, immediately you see that it's quite a long method, and the reason is that we've seen so far when we have literals, the JVM has to actually load them, all right? We treat them literal. The JVM has to literally load this. That's why you see we have this by push 10. What is this 10, right? So let me zoom in. So let's see how this initialization of an array happens. I believe we didn't look at the bytecode when we discussed the arrays and array initialization, but this is a good point to look at them. By push 10, we're using a byte integer. B means byte, integer, right? And this means it's just 1 byte, right? And what is this 10, right? 10 is actually the size of the array, So when the compiler encounters this line, it realizes that you're trying to define an array. Any array has to have a predefined size at compile time, which means the compiler has to infer it. And we said that when you do a direct initialization, the compiler looks at the elements in this initializer list and infers the size of array. So by push 10 means a integer, which is 10. And push it to the stack, and then or basically load it, and then new array int 10, obviously, which means we are creating the array. So these two lines of bytecode are for creating the array. And then and then we need to duplicate the current element on the stack, right? Because if we don't do this, then if we push something else to the stack, we lose the reference. These are more details of how the stack works, but we have to, whatever reference object reference we have on the stack, if we want to push something else, we have to first duplicate it so that we kind of don't lose track of it. iConst1, and now we've seen this before for integer literals. Basically all these are the types are integer, right? And we saw that for literals we use iConst, which means integer constant. iConst1, which means load this into a stack, and then iStore, and then store this, right? So we load this, we store it, integer iAstore, which means integer, store it, and then duplicate it, iConst1, iConst2. So basically iAstore, duplicate, iConst2, iConst3. So basically what happens here, it's what's going on. Basically after we duplicate this, we actually iConst0. So let's see what happens. And then iConst1, right? And then iAstore. Now what's going on with this? What is this doing? This line is exactly equivalent to saying that numbers at index 0 equals 1. This is exactly equivalent to these 3 lines of code. Because basically what happens in this case, the compiler does a very simple unfolding. We call this unfolding, right? No magic happens. If you write a for loop for int I equals 0, I less than 10, for example, and then I plus plus, and then numbers at index I is I plus 1, right? These are exactly equivalent with this, right? So at index 0 you get 1, at index 1 you get 2, etc. And what the compiler does with this initialization, the compiler does unfolding. So the compiler pretty much does this 10 times, it repeats this 10 times, right? Index 1, index 2, index 3, index 4, index 5, index 6, index 7, index 8, and index 9, and then 1, 2, 3, 4, 5, and then 6, 7, 8, 9, and 10. So this line of code, which seems to be relatively simple, translates in the bytecode into an unfolded version, which means the compiler explicitly writes this line of codes for you. So this is just a syntactic sugar. We call this a syntactic sugar, which means you don't have to do this. You can explicitly do it, but the compiler can do it for you if you write it like this. So again, iConst0. So obviously, as I mentioned before, when you want to do something like this, the way the JVM works or the bytecode is written is that first you have to load this index, right? And then you have to load this index, the value on the right hand side, because in the assignment you have to load the value of the right hand side. And then numbers is a reference, right? A object reference. So when we want to store something to a object reference, we use AStore. Now for arrays, because object references have a specific type for the element, there are a specific bytecodes for me, which means IAStore, which means store an integer in a object reference, right? If it was a double array, we have DAStore. So the first line of code translates into basically 3 lines of bytecode. Obviously, the next one is the same thing. We have to say that iConst1 at index 1, we have to load the index first, and then load the value iConst2, and then iStore. Basically, yes, I store the value 2 at index 1, and this all goes all the way to the last one, which means iConst3, index 4, 5, and then 6, 7, 8, 9. So here. So for the last one, we're going to get the push 9, and then index 9, push 10, and then iStore. We store them. Now you see there is a basically difference between iConst and push. iConst and push. The reason is, as you can see, all the way up to 5, we have this iConst. After 5, we don't have the const. We just say push 6, 7, 8. The reason is that these are hard-coded in the JVM. So constant 0, 1, 2, 3, 4, 5. These are hard-coded in the JVM. So the JVM doesn't need, basically, JVM can quickly access this, right? There's like a piece of memory at the JVM that has these values there. But by push, when after 5, then you end up with actually pushing these numbers. And we also saw that in the past, we also saw that there is a the -1 number is also a constant. So 0, 1, 2, 3, 4, 5, these are constant. -1 also had a dedicated bytecode iconst m1, right? And we can also check if -2, -3, -4, let's say int x equals -2. And let's go down, test 6. Let's see, so by push -2. So we don't have a constant for -2, we just push it, right? What about -1? Let's see, so test 5 and then test 6. If you look at our x, we have iconst -1. So -1 is also a constant. What if, for example, 5? If you look at 5, we see that in the x we have iconst 5. If I set this to 6, we don't get a iconst 6, right? We just push it by push 6. So 0 to 5 and -1, these are hard-coded as constants in the JVM. So it's very fast access, or JVM can quickly load these numbers as constants. Yeah. So initialization of the primitive array types, it's just a syntactic sugar for the compiler unfolds the code and writes it as many times as needed. The compiler infers the size of the array, right? So initially, there's a bytecode for a new array of type int with these elements, and then we go ahead and do this for you. All right, and then what happens to the for loop? That's the interesting part. So we are looking at test 6, and let me open this up. And then this last one, by push then and I store where the initialization ends, and then we get here all this code is for this enhanced for loop, right? So we first a store 0, remember numbers is at index 0 of the stack, and then we first load the array, right? So let's look at the bytecode for the enhanced for. We first load the array at index 0, and then we have to duplicate it, okay, because we need to save this reference later to be able to access the array again. And then a store 4, and then array length, and then I store 3, we are storing something like 3, and then iconst 0, I store 2, go to AT. AT is where we load I load 2, I load 3, and then if integer compare less than, jump to 65. So 65 is a load 4, and then I load 2, a load, I store 1, get. So there's a lot of stuff going on, so it's not really easy to understand what's going on. But the fact that we check the array length, or we get the array length, gives you a hint of what's going on, right? Obviously this means that behind the scenes this for loop translates into an index based for loop. Not exactly, but that's more or less what this bytecode is hinting at, that we check the array, and then basically we check the length of the array, and then we basically check if so at the end we're going to say if compare less than, we jump to basically line 65. Okay, so what this means is that eventually this translates into have some index, right, for the loop less than the array length. then jump to so this if integer compare less than, jump to 65 is basically we have behind the scenes the compiler creates a index based for loop, and then it tries to look at check with the array length, and if an index is still less than the array length, then we go into the body of the if statement and and then execute it, and then we come back and then do the same that we do with the for loop, check the condition again. Now let's continue with the next topic, which is the break statement. We have already looked at this, right? So the break statement has two forms, labeled and unlabeled. Now there you hardly see the format that the label is used. It's almost nobody use it, so it's most likely you see the unlabeled one. Now the topic of the label, I think they added to Java a long time ago, but nobody really uses labels because there is no reason for it. We always try to avoid nesting loops inside each other, because the whole idea of label is that when you break, you can tell the JVM you're breaking out of which loop. If you label your loop, then you can explicitly tell the JVM I'm breaking out of this particular loop, right? Otherwise, the normal function of the break is to break out of the innermost loop, or whatever loop that you're putting the break into it, right? You saw the unlabeled form in the previous discussion of the switch statement. You can also use an unbalanced unlabeled break to terminate a for, while, and do while loop, as shown in the following break. So we've seen this, right? You have the for, you put the condition here, but you can also break gives you an additional power in terms of when to terminate the loop. And although we have the condition here, we can explicitly put a conditional statement like if, and say that if this condition satisfied, then don't continue, just break out of the loop, right? So this is how, and this works for any loop, for loop, while loop, do while loop. Break just immediately jumps out of the loop that contains that break, right? This program searches for a number 12 in an array. The break statement terminates the for loop when the value is found. Control flow then transfers the statement after the for loop. So basically, once we hit the break, we jump out of the loop that encloses or encapsulates that break. Control flow then transfers to a statement after the for loop. This program's output is this. An unlabeled break statement terminates the innermost switch, for, while, or do while statement, but a labeled break terminates an outer statement, or whatever loop that you label it. The following program, break with label demo, is similar to the previous program but uses nested for loops. And again, it's usually not a good practice to nest for loops. If you can write your code in a way that you avoid nesting loops, that's always the better idea. Now, if you work with multi-dimensional arrays, obviously the easiest thing is to have a nested for loop so that we can iterate through the rows and columns. When value is found, a labeled break terminates the outer for loop, labeled search, right? And so we have a two-dimensional array, and then here we are initializing the counters for the for loop before the loop. We saw that this is possible. The best practice is to define the variables inside the argument of the for loop in the initialization statement. So this is definitely, this code doesn't follow the best practice, but it's a simple code, so maybe in this case it doesn't matter. So it's better to define the int, put the int here, so that then the scope of the I variable is limited to the scope of this for loop, and the scope of j is limited to this, right? Now the reason they didn't put it, because they want to use the value of I and j when we find the particular value after the loop terminates. So if these I and j were local variables or confined or limited to the scope of the for loop, we don't have access to them after we jump out of the loop. So this is something that you have to keep in mind. So we set a Boolean condition, and then we write our for loop the way we always write it, but then we use a label. So this label is just, you can only use it right before a for loop, and it's not a variable, it's just a label. The compiler just takes a note of this and realizes that because this is put right before a loop, like a for loop, then Basically what happens here is that uh, it just realizes that this is a label, this is not a variable, right? So as you can see, we in the inner, so we iterate over rows, then we, for each row we iterate over the columns of that row, and then if we find the element that we want looking for, we set the condition to true and then break. But this, if we don't put the label here, break just jumps out of the inner for loop, because that's the default functionality of break. But here we found the index and we want to jump out of the entire loop, right? Because we don't want to jump back to the outer loop and continue, because we already found what we were looking for. So in this case, what we need to do, we need to label the outer loop and then say break to the outer loop where the label was. And after that, we actually jump the entire break, the entire for loop construct, right? The outer loop. And you can assume that if you have more loops, you can label any of them and then break to a particular loop, right? And that's how this works, right? So the break statement terminates the labeled statement. It does not transfer the flow of control to the label. So the flow doesn't come back to the label. It's just telling the JVM that, hey, when I say break out of the loop that is labeled with this value search, right? So JVM knows that the outer for loop in this case is labeled with this label, right? Search. So it knows that when you say break out of search, it means that you're telling a break out of the entire loop. So let's quickly have a look at this labeling thing. So public static void test 7, and so let's also here run test 7. Okay, and I'm going to do the same thing here. So we have this array, and then I'm going to say that for int I equals 0, and then I less than numbers dot length I plus plus. If numbers at index I equals, for example, 6, we're going to break, right? And then well, actually we can do a sysout numbers at index I, and then we break. So we expect to see only 1 to 6 because this condition is satisfied. And we already know that how this works, but let's label this. So let's say my loop and then colon. This works, and Eclipse gives me a warning. The label is never explicitly referenced. So if you label your loop, remember, labeling only works for loops. For example, I cannot label this line of code, right? This doesn't work. Labeling only works for loops. Labeling only works for loops, while loops, for loops, etc. And I can say break out of my loop. All right. So if I run this, I should get the same result. Let's have a quick look at the bytecode. Let's open with the class file viewer, and let's look at the bytecode for test 7. So eventually we build the array, initialize it, and then basically I store one integer I, and then we initialize integer I with 0, and then go to 82. So the condition, we know that this translates, the loop translates into the goto that goes and checks the condition first, right? I load 1. We're loading integer and index 1, which is I, and then a load 0. We load the numbers reference, and we get the array length, and then we compare them. If I is less than the length of the array, we jump to 59, which we go into the body, we get and we try to execute this one. All right, invoke virtual print line numbers, and then by push, if compare not equal, right, we go to 88. Yeah, so so basically we're saying that if this condition, just go to 88. And again, this is just another thing about basically the break. In this case, we have one loop, so this label doesn't show anywhere in the bytecode, right? So it's you don't see any reference to this label. It just translates into a goto to where basically my for loop is. So I can do another thing. For example, let's put it in a for loop which has infinite iterations. It's an infinite for loop, right? And then now the label is on the external for loop. We can put it here, or we can put the label here. We don't get any compilation error. Now if we just quickly look at this, so basically in the test 7, again, now we have a goto here. If compare not equal, jump to 79. If they are equal, we go to 91, which is return. Because now when we break, if these conditions are, we break, but then we don't break basically to the outer loop. We just break entirely out of all the loops. That's why the bytecode that we jump to, if the condition is satisfied, is just return, right? Because that's when we hit this end of curly brace for the outer for loop. If I put my basically label here, now the bytecode changes in a way that when you look at the goto, if compare not equal, we jump to 54, and basically 54 is not basically return, right? So what we do is that 54 is just icons 0. Basically we jump again to this for loop and then execute the body, right? So be careful where you put the labels. The main use of the labels is when you have nested loops and you want to break out of all the outermost loop, right? Because the functional break is to only break out of the inner loop, the loop that the break is inside, unless you explicitly label the outer loops and then break out of that particular label. So I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one.